Swayam Prabha. Digital India. Educated India.
Okay, an extreme ray. So, D is said to be an extreme ray. So, D is said to be an extreme ray if D is a ray firstly to begin with. Okay. And the following implication is true. What is the implication? So, if you can write D in the following form. So, write D as mu D1 plus mu 1 D1 plus mu 2 D2, okay, where mu 1 greater than 0, mu 2 greater than 0, and D1 D2 are missed this here. D is said to be an extreme ray of the set S. Okay, if D is a ray of S, and the following implication is true. D is so if you can write D as mu 1 D1 plus mu 2 D2, where mu 1 is positive, mu 2 is positive, and D1 D2 are rays of S, then it has to be what? What should be true? Then D1 should be equal to some alpha D2 for some alpha positive. Okay. So, when we are talking of rays and extreme rays and so on, the problem becomes trivial as soon as one has a bounded set, because all these will become 0 on their own. Okay. So, these are all discussed only in the context of unbounded convex sets. Okay. So, when we are talking of so consequently 0 is really not considered a ray unless it is for pathological reasons. So, here we are talking of therefore D1, D2 etcetera all non-zero vectors. So, D, this vector D is said to be an extreme ray of S if you can, if the following implication is true, that means you write it as a conic combination, a strict conic combination of two other rays of the set, then it has to be that the two rays are actually coincident, means one is just a scaled version of the other. So, these are vectors. Okay. Yeah. So, a ray is after all is just a vector. So, go back to the definition, a vector D is called a ray if the following implication is true. That's it. So, when you are adding the rays, you just add them as vectors. Okay. Yeah. So, if you can write, if you happen to be able to write D as a conic combination of two rays, then it has to be that the two rays are coincident. In that case, we say that the ray D is an extreme ray of the set S. No, in this example, I'll need to show you, take a bit of time to determine what the extreme rays are. So, let me show you another example. So, consider, so if you just for simplicity, let us just take a cone. take a cone like this, a convex cone like this. What are the extreme rays of this set? Yeah. So, if you take these two, any of these vectors, take this vector, all of these are extreme rays, right. So, generally one does not talk of when you are talking of an extreme or an extreme ray or a ray of a set, really what you are only referring to is the direction. So, it does not, because you can scale a ray and it will remain a ray. So, all you need to really care about is the direction. So, this direction you can say is an extreme ray, right. So, all points on this direction are the extreme rays. Why is that the case? No, the cone comprises of all of these points. Okay, so let me ask you a simpler question. First, tell me all the rays of this set before we talk of extreme rays. What are the rays of this set? Yes, so what are the rays of the set? So, the set of all rays of the set is the set itself, right. All you can, because this is a convex cone, you add this is closed, this is a convex cone, you can take conic combinations of any 2 points in it, it will remain in the set. It's okay. So, you can take any point, add to it a scalar multiple of any other point in the set, that is just going to be a conic combination, that conic combination will be in the set. Okay. So, this for this cone, the set of all rays is actually the set itself. Is this clear? Okay. So, now what does this so I will just illustrate this for you. Here is a point x, for example, here is my vector d. If I have to add d, if I add d to x, I am effectively going somewhere, need to just complete this parallelepiped here. This is where my point ends up, and I can keep doing this. I can take any scalar multiple of d and I will still remain in the set, right. So, effectively I am just translating x along the direction d forever and I will remain in the set. This will be true for any x that I take and any d that you take within the set. Okay. So, in this case, this set S, since S is a cone, is a convex cone, S infinity is actually S. Set of all recession directions is actually the set itself. Okay. Now, what are the extreme rays then? Extreme rays are those that if you try to write them as a strictly positive conic combination of 2 other rays, then those, it cannot be done. Those two rays have to be coincident on each other, right. So, which means that if you take a point, say take some point like this sort of point cannot be an extreme ray. This sort of point cannot be an extreme ray, because I can always think of this as a vertex of some parallelepiped like this. This is a conic combination of this one plus this one, or linear combination of these two. So, some conic combination of these two, for example. So, if I take any of a point like this here cannot be an extreme ray. So, if you start thinking about it, you will realize that the only extreme rays possible are actually the ones, these are extreme rays and these are extreme rays. Okay, the word is well chosen, they are sort of at an extreme. You can imagine them as they are the ones that flank the cone, right. Now, this is in R2. Now, things in R3 and higher dimensions become a lot more complicated. So, for example, if I have an ice cream cone, right. This is an object in R3. What would be the extreme rays of this cone? You can see, for example, all the ribs of the cone, all the directions that start from the apex of the cone and go along the shell of it, all of those are extreme rays of the cone. Okay. So, if I likewise, suppose if I constructed a cone in R3 in which I had, say, which was not an ice cream cone, but rather say a hexagonal cone with 6 sides to it, what would be the extreme rays of such a cone? The edges that you would get, once again, the ribs of the cone, the edges that you would get from that define the hexagon, those will be the extreme rays. Anything along the surface like this, which on a flat surface is not going to be an extreme ray, because it would be, you can write it always as a combination of two other extreme rays, right, two other rays. All the rays of the set S can be written as a conic combination of all other rays. The answer to that is yes, but I'll explain in a better way, because this becomes this sort of statement is it anticipates what I want to just say, and it's very sharp, can be made very sharp for polyhedra. So, let me come to that point now. Okay. So, what we were building up basically to what is called the Minkowski-Weyl theorem. This theorem is due to Minkowski and Weyl. So, in the previous class, as I was leaving, I asked you to imagine what a bounded polyhedron would look like. Right? A polyhedron is an intersection of half spaces. What is a bounded polyhedron? How does that look? Not a polygon. So, a bounded polyhedron would look something like this, right? It would look like a set like this. Okay. This is, for example, not an bounded polyhedron, but what do I mean by it looks like something like this? What's special about this set? You take any point in this set, right? You can write it as a convex combination of these red corner points or red extreme points, right? So, once you have a bounded polyhedron, you can just look at its extreme points and you can generate the entire polyhedron by taking convex combinations of those extreme points. Okay. What if you have a set like this, which is not a bounded polyhedron, but an unbounded polyhedron? Now, it is not true anymore that this set has just two extreme points. Now, it is not true that every point can be written as a convex combination of these two red points, right. There are points here, for example, which cannot be written as convex combination of these two. So, what is the analogous extension of that earlier observation? The observation is that if you have a bounded polyhedron, then its every point can be written as a convex combination of these fixed points, these extreme points. Plus, yes, so you have what were you saying? Very nice, very good. So the thing that he has anticipated is actually the statement of the theorem. See, if you have a point like, if you have a polyhedron like this which is unbounded, and take a point like this here, okay, take this point x. This point cannot be written as convex combination of just the extreme points, but it can be, what he is saying, that it can be written as convex combination of the extreme points plus translation with the rays that you have in the set. And in fact, you can take only it is enough to take only the extreme rays of the set. Okay. So, this is basically the main observation, and that this theorem is that this theorem is talking about. Okay. So, I will just state the theorem for you. every polyhedron P. Okay. So, suppose you can polyhedron, I am going to represent it in the following form. I am going to represent it as x in R n such that A x is less than equal to B. Can be represented in the form sorry my mistake here. So, I need to tell you one blanket assumption that under which this holds, and I have not stated here. So, every polyhedron, so we are talking of polyhedra here that have extreme points, that has an extreme point. So, every polyhedron that has an extreme point can be represented in the following in the following form. So, the polyhedron is actually the is in the following form. Every point in it is a convex combination of points x k, where k ranges over a set capital K, and plus a conic combination of points x r, where r ranges over a set capital R. Okay. Now, here the points x k, where k belongs to capital K, these are the extreme points of the polyhedron, and x r, where r belongs to R, are the extreme rays. Okay. So, what this means is you just take the convex hull formed by the extreme points of the set. Look at also the cone generated by the extreme rays of the set and add the two together. That actually gives you back your polyhedron. Okay. So, this is what the statement this theorem says. This is true provided the set has at least one extreme point. Okay. So, you take a so equivalent way of writing this equivalently. P is equal to the convex hull of the points x1 till points xk, where k belongs to convex hull of points xk, where k belongs to capital K, plus the cone generated by points xr, where r belongs to capital R. So, every polyhedron has this sort of can be represented in this kind of form. So, this is an extremely important theorem, because it gives us in one shot a way of viewing all polyhedra. Every polyhedron is basically a polytope, which is a bounded polyhedron created from just the extreme point, translated along the cone created by its extreme rays. Right. So, to describe a polyhedron completely, all you need are the base polytope that is formed by its extreme points and the extreme rays that are there in the polyhedron, and translate the base along the directions defined by the cone, and you are done. That's how you describe a polyhedron. Okay. This is an extremely difficult, complicated, powerful theorem. It also seems very intuitive, but it's actually very hard to prove. It takes quite a few pages to actually do the proof. Okay. So, the way as I said, you go back to this sort of this kind of a set here, this sort of set, the way this what Minkowski-Weyl theorem is saying is that the way this set is generated is that you take the convex hull of the extreme points, which is just this segment, and keep translating this segment along the two extreme directions, the two extreme rays. What are the extreme rays in this case? This and this are the extreme rays. So, you take this segment, translate it along this direction, translate it along this direction, that will basically generate for you, or translate it along the any direction that is formed by a linear convex conic combination of these two directions. Take this direction, take conic combinations of those, translate it also along those. All of that put together will give you the entire polyhedron. This yeah, I am just I mean, one would have to calculate this, but yeah, to me it looks like this ray and this ray would be extreme rays. Which one? If you take a ray below it, then it will not be a ray of the set. Yeah, the one inside is not anything inside here is not going to be an extreme ray.
Yeah, no, what I am seeing this ray is actually horizontal ray, which is the bottom one, will be represented as combination of two rays inside the.
Which ray are you referring to? The one here, this one?
It's draw a straight line inside the cone, straight horizontal line.
Okay, let's I can do it, but this one. This is if it's inside if it's in the interior, that's not. So the extreme rays are these, the ones that I am calling extreme rays are these directions. Okay, so that gives you. So that's basically that's Minkowski-Weyl theorem. Now, why is this so important? Is because it actually in one shot gives us also a way of understanding what happens in the first kind of optimization problem with inequality constraints. So,